Okay, now let's put some values to these, right? Now we're going to find the area, so we can generically look at that. But remember, we talked about that net area. So we're given this function, f of x. This little section here is equivalent to 12. This little section here is equivalent to 10, and this section is equivalent to 8. So if I am asking you to integrate from a to b of this function, you always have to have that differential, dx. What is that going to be? From A to B, what is the area? It is 12. And that's legit it. Okay, what if I want to integrate from B to C of my function? What is that? That is below the x-axis, so what is that net area? Negative 10. It is okay to have an area of negative that represents below the x-axis, right? It represents below that x-axis. All right, this is stating above the x-axis. This is below the x-axis, right? Okay, let's squeeze this in here a little bit. What if I want to find the integral from A to C of my function? What's that? Yep, I've got this piece which is positive and this piece which is negative. So I have 12 minus 10 giving me 2 net area. Interesting, right? Yes, because you have the positive above, the negative below. That's the moral of that story. One more. What if I want to integrate from B to D? B to D. Yep, you've got a negative 10 and a positive 8. Yep, negative 2. It's literally that easy. Good. Good, good. Nice. So looking at all different kinds, if it's above the x-axis, it's positive. If it's below, it's negative. And just put them together depending on what it is you're looking at. Yeah. Cool, right? Okay. Now there's one more thing in this section that they talk about, which we need to go over because it's important. We're not going to use it a whole lot this section, but we're definitely going to use it moving forward. Why they put it in this section, I don't know. But it's important to know. You need to know these, so we're going to go through them. They are the integration properties. All right. So, number 1. If I am integrating from B to A of f of x dx, if you end up with this b here, because I'm on the interval from A to B. So when I integrate, that's a tongue twister, isn't it? And I have my bigger number here on the bottom. You don't want your bigger number on the bottom. You can do this and switch the sign to be a negative in front, and then you can switch your bounds. That's a big one. If it's a bigger number on the bottom, you want to switch those bounds. You always want to go from small to big on your integrand, is what that's called. This symbol is an integrand. So you always want to go from small to big. If that's not the case, then you want to swap those. You just change your sign out front. If it's already negative, you change it to a positive to swap your bounds. If it's positive, you change it to a negative to swap your bounds. All right? Okay. If I am integrating from the same number to the same number, what kind of area do you think is going to be under that curve? If I'm starting and stopping at the exact same number, yeah, there is no area. I'm starting and stopping at the exact same number. There is no space under that. There is no area. Okay. If I'm going to go from A to B here of f of x, and I want to add or subtract g of x to this, the same thing applies like we did with our derivatives, like we did with our limits. This all goes together. So there's nothing brand new with integration. All the rules in terms of adding and subtracting are going to be exactly the same whenever I have this. So I can split this up. I can take the integral here of f of x, and I can add or subtract that to my integral here of g of x. Okay. We're not going to write it out like that. Just like we didn't with our derivatives, we just did it all at once. We're going to do that also here. But this is the concept. This is the property. I'm going from a to b of a constant times my function. Guess what? We could pull the constant out in front just like we've been doing this entire time. It's no big deal. The constant is just multiplied by the work you do. Still is. Lastly, you can actually split up an integral. If it's kind of wonky donkey as you're going through there and it's easier to work with this as split up, you can find some value in the middle here. We're going to call it p. So I'm going to go from a to p of my function plus, because it's just area, right? P to b of that function. I'm just saying I want to find this area under the curve, whatever it is. I'm going here from a to b, and then there's some value in here of p. So I can split this up and have this area over here plus this area. That's all that's saying. What is a definite integral? The area under the curve. So I can split up and just add those two areas together. Right? Okay. Nice. That's it. That's what we're doing. So here's our properties that we have. We're going to come back and touch on these later. The properties are going to make more of an impact moving forward, but it's good just to have them out there so that we're looking at it. Okay, great.